So today we're going to be looking at a closed tank and the flow rate, or more specifically the change in height of the liquid inside the tank with respect to time, given a small outlet. And for now we're going to ignore most of the numbers because we're just going to plug them into a Python code that we write after we derive the necessary equations. So we're going to start off with Bernoulli's equation, and before we solved for an open container, and we've basically been able to ignore this term because we assume that the pressure inside the container, or specifically in this part of the container, is going to be equal to the atmospheric pressure, so this term would obviously be zero. In this case, we're going to seal the container and say that the starting pressure is atmospheric pressure, but then from there it's going to vary because we have the same number of moles of gas, or the same number of moles of air, but the change in height of our liquid is going to lead to a change in volume, which is going to change the pressure. So the first thing we need to do is determine an expression for the number of moles we have. So we're going to be starting off, we're going to need the initial height of the fluid, we're going to need the cross-sectional area of our tank, and this is assuming that the tank is uniform, and then we're going to be needing the starting pressure, and for now we're just going to assume that it's atmospheric pressure. So we have N equals PV over RT, and all we have to do is substitute. We'll also be given the starting temperature, but we'll leave that as a parameter we can enter into our equation in Python, just so we can vary it and see how things change. And more specifically, that's going to be P1. In this case, we're going to say that P1 is going to be equal to the pressure at our outlet, the pressure external. So P1 equals P external, which is just going to be 101,325 pascals. So we can go ahead and plug that in, and it is going to be equal to 101,325 pascals. And then our volume is going to be our total height, H, minus the height of the fluid, or the initial height. So we're going to have our cross-sectional area and our height minus, I'll make this big H because I like using big letters for totals, but anyways, minus our initial height. And then that's just going to be equal to over RT. So now that we have an expression for the number of moles of gas, this is going to stay constant. So if we vary the cross-sectional area of the cylinder, of the tank, the starting height, the total height, the temperature, these are all things we can change. And actually, if we wanted to, and you know what, I think I will do this. We can also vary the initial pressure of our tank and leave that as a parameter that we can enter as well. So that's going to be our number of moles. And from there, we need to come up with an expression that we can use to express the value for P2. Because we know P1 is just going to be whatever our initial pressure is. And in this case, and the numbers we're going to be plugging in will be 101,325, but I'm going to leave it open-ended so we can vary that if we'd like to. So from there, we have P2 is just going to be N RT over V. And then this volume is, of course, going to be changing with respect to time. So we're going to need to express this in terms of a derivative, but we'll come back to that. So P2 equals nRT over V. And then this V1 is going to be 0. There's no initial velocity. So from here, we just need to solve this algebraically. And I'm going to leave things in variable form. I'm not going to substitute because this is all stuff we can do in Python. We can just define expressions for each of our, or define variables for each of our expressions. So it'll it'll be cleaner, I think, later on. So normally Bernoulli's equation would be equal to fancy F, or frictional heating factor. I am really bad at drawing it, so we'll come back to that after I've had some more time to practice. But for now, we know that our height, we have to choose an initial height for our fluid, and we're just going to say the height at the bottom of the container is 0, and it goes up to h. So this is just going to be, or really it'll just be, no, it'll just be h. So it'll be g times 0 minus h, or just negative gh. So the full expression will be P2 minus P1 or Pi, and I'll try to be consistent with that, minus P1 over rho plus V2, again because we don't have an initial velocity, V2 squared over 2 minus gh will be equal to 0, and then we just need to solve in terms of velocity. So we have, we'll have v2 squared over 2 equals gh, and then these will flip when we subtract them, so it'll be p1 minus p2 over rho. And again, we could substitute our equation over here. And actually, I don't know why I skipped this before, but our volume, we can express it in terms of our the height of the liquid and the cross-sectional area. That'll just be well, like I said, it'll just be our total height minus the current height of the fluid times our cross-sectional area. So our final expression for that will just be P2 equals N RT. And again, we defined the N up here, but I'm going to leave it in that form just so it's a bit cleaner when we do it in Python. So we'll have nRT over big H, the height of the container, minus little h, the height of our fluid, times the cross-sectional area of the container. And this is the difference in height between the two. So this is the pressure of the gas. So anyways, back to what we were doing. We'll have GH plus P1 minus P2 over P. And we can just multiply across by 2 and take the square root. So we'll have V2 is equal to the square root of 2, and then GH plus P1 minus P2 over rho So the last little bit we have to do here is just define how we're going to find the change in height. So first thing we can do is say that our Q out, our flow rate out, is going to be equal to our velocity V2 times the area of the outlet, cross-sectional area of the outlet. Ambulance outside, don't know if you can hear it. And then from there, we know that the change in volume, I'm going to write it out because we have a lot of these floating around, with respect to time is going to be equal to negative Q out, because obviously the change in the volume of the container, or the liquid inside the container, is going to be the opposite of the volume that's leaving the container. And then to change volume to height, we know that V is just the cross-sectional area. AC times the height of the fluid. And in this case, we know AC times H. So to get H, all we have to do is divide by AC. The volume by AC, so V over AC equals H. I'm going to notate it like that. It's not entirely accurate, but just to keep things a little separate. So then all we have to say is the change in H with respect to time, which I have no idea what I did that. Not necessary. The change in H with respect to time is going to be equal to negative Q out over H, or sorry, not over H, over AC, which will just be V2 over, or V2, that area of our outlet, over the cross-sectional area of our tank. So just to recap, we have our, this expression for the number of moles, and we're going to leave it in variable form, not define it. Well, we'll test it with the starting pressure, but I'll leave it open-ended so we can change the starting pressure. And obviously the initial height, the temperature, cross-sectional area, all of that. We'll have our expression for P2. And then from there, we'll have our expression for V2, which will be in terms of our other two expressions. And then we'll have our expression for our change in height with respect to time. So all we'll have to do in Python is put these expressions in and create a function that will loop through it and plot the change in height over time. So now to code this in Python, we just have to put our expressions in and then make a function that'll take time as our input, so we can iterate through it using our numpy solve IVP, or sorry, scipy solve IVP. So we can iterate through it with that, and then I'll also be taking in our initial height as a vector. So the first thing we're going to do is go ahead and put our equation in for n. And you can't see my screen right now, but the number of moles we have is just going to be equal to our pressure initial times our cross-sectional area times our height of our tank minus the initial height of the fluid, all divided by our gas constant times the temperature. And actually, the temperature doesn't matter, because if we were to plug this in, specifically if we were, let me pull it up. If I can find my cursor. Here we go. So if we were to plug this in, our n here over RT, it would cancel out with this RT here. So we actually don't need that. So I'm going to go ahead and rewrite our equation without that RT in. And then that means we can also get rid of one of our inputs, because really it doesn't matter. So we don't need our R anymore, because that's going to cancel out. So let's see. N is going to be equal to P1 over RT. Looks like I'm just going to be writing the equation for our P2. So our P2 is going to be equal to nRT, and again, the n will cancel. So we're going to have our PI, our initial pressure. Let's see if I can, there we go, times our cross-sectional area. I'm going to be typing really slow because I have to type around this drawing tablet. And that will be times our height of our tank minus the height of our fluid. And that all will be divided by the height of the tank minus the current height of the fluid times AC. And let me clean up the parentheses here. And I think there's going to be, yeah, we can cancel out these two cross-sectional areas. So we'll go ahead and do that. And then we can just plug this in to our velocity equation in place of P2. And then I still left our initial, the initial pressure inside the tank up to the user. Let me double check that the parentheses are correct here. I have an extra set that I don't really need. And that looks good. Forgot to run this. There we go. Okay. So then we need to define our right-hand side of the equation here for velocity. Yeah, I'll just leave it as RHS. And we're going to be passing in a time just because we need something to pass in. And then we're going to be passing in a vector, which we'll just call y for now. And we're just going to set our height, that's changing over time, as our first value of our vector y. And you know, I don't need this anymore. Let me get this out of the way. I don't know why it got that small. And then we just have to write our expression for our velocity. So it turns out I should probably keep my notes up here because we're going to be using them. Hold on, let me window these. There we go. And then we're going to be moving this inside of here because we're going to be passing in our h as our vector, or more accurately, solve IVP is. So go ahead and define P2 there, and we can get rid of this. All right. And then our h is defined, our hi is defined, and our pi is defined, so it looks good. And then we're going to calculate our v2. Just going to be equal to the square root, and we want to take the absolute value of the square root. And then we'll do 2 times our gravity times our height plus P1, or P initial, that's how I wrote it, plus P2 divided by our rho, and then we toss in the parentheses here. And then we need one more closing parenthesis. And then we're going to return our V2 times the area of our outlet, or actually I wrote it as the area of the hole, divided by our cross-sectional area. Okay, and then from there, we actually want to return this as a list because solve IVP is meant to work with iterables or lists or arrays. So we're going to return it as an iterable, and then I just forgot a negative sign here. And then from there, it should work. So let's go ahead and test that out. T doesn't matter. It's just a random number. It's not used anywhere. And then our y, we'll set that to, I don't know, 0.8. And there we go. So that is the velocity at that, or sorry, the change in volume at that precise time. So then what we need to do is set up our solve IVP, and our result is going to be equal to solve IVP. And I'm going to go back and reference the syntax for this, and I'll be right back. So it turns out what we need to input is our function that we're going to be solving for. We're going to be providing our t-span. Oh, that's a neat feature of Colab that I kind of forgot about. But our t-span is just going to be from time 0 to t end. Our starting value is just going to be each high, and we need to input that as a vector. We're going to be using the redo method because it was recommended by my professor. And then we're going to be doing something. Well, first off, we need to do dense outputs. But we're going to be using the events feature of solve IVP, because if we were to just input this as it is, it would cycle through until it reaches steady state, and then it would be constantly redoing the iteration, but subtracting a smaller and smaller number over time. So even though it reached steady state, eventually our solution would go haywire, and it would decrease in value exponentially. So the way we're going to avoid this is by creating an event that will terminate our solve IVP when the value of the velocity equals 0. So we just need to create a new. Let me move this down. We need to create a new function, and I'm just going to define it as event ty. That's going to be our inputs. And then all we need is this value in here, because if this goes to 0, then obviously our value for the velocity is also going to go to 0. And that's what we're going to be returning. And then we also need to provide it with the same inputs that we provided it before, just so it'll run properly. And when this ends, we want it to terminate the program. So, well, not the program, but solve IVP. So we're going to set event.terminal. The dot terminal is the thing that's actually modifying or setting the parameter for our event as terminal value. We're going to set that equal to true. And then I can't quite remember the syntax for this, so I'm going to go ahead and guess. But I'll check it again off camera and come back to you after I put this in. But we want to put this in as a vector. Darn, thought that might work. So I did a bit of off-screen troubleshooting. I thought maybe it had to do with just naming our event, but I think it's actually because I forgot a parenthesis. So we'll see if this works. Yep, and it should work here. Looks good. And then all we have to do is plot this over time now. So our t-plot, and actually let me show res so I can talk about what I'm doing. So we have this t event here, right here. And if you'll notice, it's an array within an array. So we want our t-plot to be linearly spaced. And we want it to go from 0 to our end time. And the way that we can reference that is just t events res dot t events. I mean, I figured I was forgetting something, but I forgot we just need to reference res. And then we're going to be taking the first item from the first array. And we'll do 1,000 space points. Let me try this with just. There we go. I guess we don't need to reference both, which is weird because I had done this earlier and we did. So I'm not sure what changed. If I find out, I will definitely add it to this video. But anyways, we're just going to run with this. And then we're going to make a subplot. So off screen, I had quite a bit of trouble, an hour's worth of trouble, trying to figure out why my event wouldn't work. And after a bunch of troubleshooting, I realized I made a mistake all the way back here with our algebra. I said P2, or our final pressure, is going to be equal to nRT over V. But in reality, that is our initial pressure. Our final pressure is going to be equal to our external pressure. So that was what was causing the issue. Actually, if we look at what I wrote down over here, this should be a minus as well. But yeah, that should be a minus, I think. No, that's fine how it is. But the reason that I was having issues with it was because I basically flipped these two, and the way I had it written, it was never zeroing out. So over here, I had either P1 minus P2 or minus P2 over P1, I can't remember. I just needed to flip it. So now, if we go ahead and take a look at this, we can see that our T events has a single array here. Well, it has a nested array. And we want to just go ahead and take the first value of the first array when we're making our T plot. And then if we want to take a look at this, and if we do res.solution and then use our T plot as an input, it's going to give us the solution for T at every single one of our values in our T plot. But another thing you'll notice is that it's giving us the nested array again. So to get the solution of res for every value, but we only want it as a singular array, we just have to indicate index 1 or index 0, but the first index. And then we can go ahead and plot it. So like I was saying, make subplots. We add a scatter plot, and then x is going to be equal to t plot. That's just going to be our x-axis. And y is our solution for res at every value of the t plot like we did up there. And ta-da! We have a graph over time, and then once it reaches steady state, it goes ahead and ends the plot.